Alright, I built this little CCS. I was going to actually do a bunch of CCSs as part of one video, but I did a lot of investigation on this, so it sort of warrants a video in and of itself. Um, you know, this right here is the circuit I built, right? So it's just like you see in the simulation here. It's a dual transistor CCS. Um, and I was just simulating it to see what the exact effects were, but it's set to approximately 2 milliamps. And you can see on my fluke there, I'm measuring the actual current. It's a fluke 89 4 series, or 89 IV. So, and here is the voltage I'm applying to it, 30 volts exactly. And I'm measuring the voltage across this O1. Damn it. I keep hitting my leads with this camera, so every time this is kind of a dodgy setup, but every time I do the meter readings change. In fact, I discovered that some of the ranges on my with this test, I discovered some of the ranges here are bad. Some of the resistors got overheated at one point or another, and when resistors get overheated, they change. They tend to diminish. So, and this is kind of the results of this. But again, I ran several extensive tests. But anyway, this is me testing my resistor box using this constant current source to predict the resistor. So value, and you can see how out of whack some of these things are right here on the spreadsheet. So like the 2K is totally fucked, and the 10K is totally fucked, and then the 4K ain't great, but it's still within a 5%, so it's still usable, but it's supposed to be 1% resistors with 0.02 ohm internal, and actually it's 0.1 ish, as it turns out with a CCS. But anyway, this CCS at 30 volts could probably go up to about 15K pretty reliably, but I have see, I tested that up here. I took it to about 14K was the max reading I took it to with that same voltage setting. But again, you can see that it's got 28 volts across it. It's a 30 volt supply, so it's getting close to its limit there. Now, by the way, let me put the camera down here. This CCS I built based on what Elliott Sound Products little article is on, current sources, sinks, etc. He's got an article on this, so you can go pull it up. I made a PDF of everything that I read on his site, just so I have a backup in case his site ever disappears. He's getting up there in age. So, but anyway, yeah, I basically built this CCS pretty much using the values he used. So he ran his at 20 volts. I wanted up mine at to 30 just to get increased range. But yeah, he basically, goes in and, talks about it rather extensively. And in fact, this whole article's got really good CCS stuff. I'm going to build some more stuff from it too. But this is basically the model I'm using. This is the data he did. Now, you got to understand something about a lot of his stuff. A lot of his is based on simulations. The problem is he didn't tell me what transistor he used in his simulator, so that doesn't help. But again, I'm getting significantly different results, than he got. And but again, while he does base a lot of things on simulation, it's usually tempered by his own vast experience. So You know, in other words, he knows usually when something's bogus or not, although sometimes some things like this might be a little out of his wheelhouse, because, but maybe not. I mean, depending on the transistor he used, I don't know. I don't know what the effect of, because I, you know, base this off of a, PN 2907, so, you know, two of them. So, I don't know what he based his off of. But, but the values he's getting, calculating the apparent impedance, are pretty remarkable, and mine don't come anywhere near that. In fact, let's see, because you can see on this test, it's really difficult trying to get these values nailed down because they're a little squirrely. Because this thing tends to change a lot as you're changing the values, because the bigger the voltage drop, the more of a load you put across the transistor, the more it heats up, that changes their beta, and so there's a kind of a cascade effect there, so it can be kind of hard nailing these down unless you want to sit there for 5 or 10 minutes between each and every measurement. So these I did just as fast as I could. These took longer, so they're a little more dubious in my opinion, but that's the calculated value of resistance. This is its estimated impedance, in other words, what it appears to be like, in terms of how much resistance it is. You can see most of his are like 7.7 meg, etc. Mine, were all over the map. You can see that several of these were well over a mega ohm, but some of them weren't, and, sometimes that's, it's hard to say. It's because of, this thing being so transient. But, it still shows, that, this is a constant current source. Still acts like a pretty large resistance, 1, mega ohm or more is pretty good. Let's see. Jeez. I guess I never calculated the average value on, oh, I did, down here. Okay. Yeah, so 1.3. Yeah, 1.3 mega ohms is the average value of this thing. So, was the average impedance value of it. So, that's quite a bit, that's reasonably stiff, and let's see, 1.98 milliamps was the average current, over these readings. So, and here's the maximum, was 1.98, and the minimum was 1.97 over this set of readings. So, standard deviations right here. So that's like an RMS version of variance. Variance isn't too useful for something like this, but so, I mean, it still performed, alright, alright as a two random transistor current source. I made no effort to match these whatsoever. So, it's interesting results. Let's see. Now here what I did, and I guess I haven't labeled this yet. Let me, so I'm stumbling around a little bit. I'm a little confused because I didn't fully annotate this thing properly. Make sure this is the right date. Yeah, okay. Go ahead and put the label on this real quick. Oh, son of a bitch. Okay, so constant resistance damn it, temperature variation. So basically I ran a series of tests, and you can see the times, I took each and every measurement. This is the temperature, of each and every measurement, and these are the measurements themselves that I took here. These are all calculations based on these measurements. So this is the real data right here in these two columns. But you can see basically, we had a variation over, this temperature range. So, of like 9.61 degrees centigrade. So, we had this amount of voltage variation, this amount of current variation over that same fixed resistance setting, and then, this amount of resistance variation, because we are going to see a variation in resistance. These are, like precision, metal film resistors, so we're looking at 200 parts per million, so you'd expect a variation of like 21 ohms, over that temperature range, but in fact we got 17.62, so that's a little better than spec. So, and like I said, this 20 microamps works out to, basically 2.08, shit, god damn it, 2.08, motherfucker, I hate this, oh, motherfucker, that's one of the disadvantages of having a 4K monitor, by the way. It makes your mouse a lot less precise, so it's really harder to actually do things with it, because it just doesn't, it's like it's not tuned right to it or something. It's like tuned to a 1K monitor, not a 4K monitor, or a 2K monitor, not a 4K monitor. Anyway, yeah, I get really frustrated with that crap all the time, just trying to do things on this computer. But at least I have like 4 times the display area I normally have, so I can't bitch too much. But bitching's what I like to do. So anyway, but yeah, we had about a 2 microamp per degree centigrade, estimate, over, with this one particular resistor over this 10-degree range. So, so again, I don't think I'd want to apply it too much outside of this range, but I mean, for this range, that's our estimate. So again, based on that, we should have had about a 0.22 volt variation if it were just for the, CCS alone, and that's about what we got. That's about the variation, so that's predicting that. So, and like I said, we covered the resistor variation, so like I said, I couldn't locate any data about the variation in current, based on temperature for my meters, the Fluke or the O1. I'm sure there will be one, if you had an exactly constant current source fed into it that was stable over all temperature ranges measured over, you'd probably see a difference in your reading based on temperature, because almost certainly there will be some effect. So you can't assume zero, but for this case I had to assume zero effect because I can't find any data on it. Even reading through Fluke's extensive specifications, they still didn't mention anything about that I could see, or that I noticed. But at any rate, so down here to kind of test this further, I went in and fixed it. I wanted to see what its variation with voltage would be, so I was trying to target approximately a 1/4 volt variation. So I went, and configured it with the same resistor values, but then changed the resistor values a little bit, to give us a certain variation in voltage. And you see, here was the nominal voltage right there. That was when I started, but then I took this reading here and this reading here. I was going to take a smaller one, but given how fucked up my resistor box would be, that would have been an enormous pain in the ass, since it is, not perfect at the moment, so I'll have to repair it. But I took this reading, which is what I was looking for, but I took another reading at a slightly higher voltage just to be safe, so to give me a third data point anyway, so I could validate it a little better. So, at the end of the day, it should be about 1.4 microamps per volt, or 3.25 microamps per volt, is the expected variation. So, you know, so basically, going back to this amount of voltage drop, you'd expect it to only be about 0.74 microamps, instead of 20. So, or actually, I don't know if that's right. It's probably milliamps instead of microamps. Um, hold on. No, that's right. I mean, it's like I said, we actually measured here, about 1.4 microamps. That's over, about zero point 0.4 volts. So, yeah, I mean, you'd expect it to only be about 0.74 microamps based on the voltage range here. So, I mean, it really shouldn't have deviated by that much, but yet it did. It varied by over 20 microamps. So one can only conclude that most of the variation you saw was directly due to temperature variation on the constant current source itself. So, basically that tells you sort of what you can expect, at least with this particular transistor and so forth. Again, I don't know if other transistors would produce different results. Like if I put a Darlington in there, I mean, I imagine that'd be a hell of a lot worse because, it's got so much more gain, and therefore its beta is going to be more temperature sensitive because you got two transistors in there with beta variation due to temperature. So, I mean, hypothetically, the lower the gain the transistor, the better, and that's why this might be a better transistor because it's a little lower gain than like a 3904 or 3906, I think. So, so I don't know how those would perform, but at any rate, yeah, it was an interesting investigation, just because I've always been curious about these kind of constant current sources, but I never actually built one because every time I ever read about any of them, they say, oh, you've got to use matched transistors and shit. Well, it wasn't until Elliott Sound Products that I, realized that, shit, he does crap like this all the time in his circuits. And most of the time, it doesn't matter, it doesn't have to be ultra precise for a lot of his applications. So, yeah, he regularly does things like this, in many of his circuits. So, at the end of the day, no, you can make a useful constant current source with these. But again, I've always read that no, they're going to be matched transistors. Use the, some, $25 part, to, to get matched transistors. And and it's just been kind of annoying. But no, you can, you can actually do it fairly well. This is the first, real investigation of a CCS I've done. But I've always been curious, but I've always shied away from them because I thought they just wouldn't work right unless they were on a, a silicon die. So, and I really, in the past, like 20 years ago or whatever, when I was more inclined to do investigations like this, I didn't have good equipment, so it would have been kind of a waste of time, and I knew it. So, many years passed, but now I'm back to it, and I'm gratified I finally got to be able to do this sort of analysis on it. As a CCS, to try to evaluate different CCS. Because, CCS is a valuable thing to have, and, just finding out how fucked up my resistor decade box is a good example of that. Of course, I could have done that with an ohmmeter, fairly accurately, but it's nice to be able to use it for things like this, and, there are many other applications, that a good, stable CCS can have, particularly if you can make it go lower than this, the microamp range and everything else, and make it stable. There's lots of sensors you can get readings on and everything. That's kind of the whole point of buying that SG003 or whatnot, that loop tester, that I made a video about, is, for that's one of the reasons I was kind of inclined to buy it, and certainly it has that advantage. But if I wanted to build my own piece of test equipment, like something, I don't know, that could send that data to a PC like that damn thing can't, yeah, I mean, it would be nice to be able to build constant current sources. And he's got a really interesting one in one of his articles. He builds this, low ohm multimeter, not multimeter, but it's a low ohm meter. He has a separate article attached. It's like one of his projects. And in that, he has a current source, you know, a constant current source he built, which looks intriguing. You know, that can go up to 1 amp, and, you know, but like 1 milliamp, 10 milliamp, you know, 100 milliamp, and 1 amp, something like that. But at any rate, it's, you know, pretty neat. Its current source alone might be worth building, you know, to evaluate it. But of course, that's way more elaborate than something like this. But at any rate, I might go ahead and, you know, make this up into a little strip-line circuit board, you know, just to keep it around as a handy reference using these, you know, particular parts, you know, so if I want to do any further, and this capacitor, by the way, is not part of the circuit. I just have that there so I got something stiff to attach my leads to, my test probes, because I actually do have the analog discovery hooked up to it, because of course I want to see if it's noisy or not. You know, you never know about these things sometimes, but it seemed pretty decent. So, but at any rate, that's about all there is to it. I do have some other CCSs to look at later, so until then, cheers. Oh shit.